Today we're going to see about entering in our values for the pins and explore some of the settings within UCCNC in order to create a custom profile to be used as our CNC controller. When you open UCCNC, it may ask what default profile you would like to open. It does not matter because we are going to make our own. The first thing we're going to do is create a profile. Also, we will create a shortcut to be used to open UCCNC from now on. Your appearance may not look like this. However, if it does, the first thing we want to do is select Configuration and then Profile. Click on New Profile Name and type your machine name. Be sure to click Enter or Tab to make sure your typed info is entered. Check to create a shortcut. Then click Create New Profile. We will then close the application to open it through our shortcut. You can see my test shortcut was created. So I am going to delete the original UCCNC icon. The next thing we are going to do is a personal preference, but we are going to select the screen set. Open the shortcut. Under Configuration and Profile, we will click Select Screen Set. I like the organization and the dark look of the 2019 set. Choose and then hit Select. The application has to be restarted in order for this to take effect. If your default screen set looks like this, however, we will change it within the Settings tab, then Appearance. In order to create a profile, it is the same steps under Settings than the profile selection. We are going to go tab by tab, and I'll explain the functions of each. The first tab is going to be Offsets. This can be used if you have different fixtures. The active fixture is represented by G54 through G59. It's easier to say they represent different origins that can be saved. In order to change our active fixture, we will select G54 through G59 on the bottom left of our page. The next tab is the Tools tab, which is used when the G-code utilizes tool number for the offset or G41 and G42 in the tool number. Since we use this as a plasma cutter and a plasma arc is not a perfect circle while cutting or as consistent like an end mill, I like to use the option in Fusion 360 to generate the compensation in the computer. However, if we were to be using the tool numbers, we can designate the tool offset and the tool diameter to quickly change how the tool cuts. This is especially helpful for milling. Let's say tool 1 is always half an inch in mill, however the tool is at the end of its life and cutting oversized. This is a way to change the diameter cut and offset without generating a new G-code. Within the Tools tab, we have a digitize setting, which is much like a probe. However, the offset or the probed surface will be saved. This is much more handy for something more precise like a mill. But since we use a floating head to probe, it is better to touch off before every cut. We then have a camera setting which allows a camera over USB to be utilized in these software. Then there is a User tab, which allows a personalized screen layout. I am unfamiliar how to add and change to the user screen, since I have never seen a need for it. The next tab is Probe. Looking at page 1 and page 2, it explains the different types of probing actions and centering offsets that can be utilized. This, however, in our case is overkill, since a plasma cutter will not be accurate to that tolerance. The setup selection is at a range of settings and clearances that can be utilized to better personalize the probing actions. The next tab is Settings, which will control the pin input and outputs. In the general settings, we have the interpolation mode, which is how the controller is going to approach corners. Exact stop means the torch will go all the way to the corner, and stop to continue the movement. Constant velocity is when the torch tries to keep moving over the corner will end up rounded to keep that constant velocity. It will follow the set parameters below. We then have how UCCNC will respond to any unknown G-codes. Input debounce is a delay for the input after the signal is received in order to account for any variance that may be found. Below that is the order you would wish your home sequence to follow. I do not utilize homing for my CNC. Lastly are the settings under kernel frequency. Kernel frequency is essentially how many pulses the computer or the board must utilize over a given amount of time. With the AXBB, we can select any frequency. However, with a CNC with more functions and a higher demand, a higher frequency would be desirable. Also, it is important to note some components or boards require a certain kernel frequency to function. It is important to remember to save and apply settings as we move along. Next is the axis setup, which is fairly straightforward. I will use the Z-axis as my example. In my Word document, we can see pin 15, 16, and 17 are used from port 1 for the step, direction, and enable pins. Active low for the direction pin will cause the motor to spin the other direction. I have an active low setting for the enable pin, which gives me the desired effect. The values entered will be calculated for your machine. Also, there is a quick way to calibrate your steps per unit in which you will tell the machine to move so far and then measure how much it actually moved. Then, by dividing the entered values, it will calculate a ratio to multiply the steps per unit and get a closer value. On the right-hand side, there is an option for slave axis, which should work by mirroring movement to the selected axis. On the spindle setup page, first thing we want to do is select whether it is a PWM spindle type or a step direction type. Since this is a plasma, it is neither. So the only thing we have to change is on the right-hand side where it says M3 and M4, we change that to our output pin 8. Utilizing the Word document, you can see the input values needed for the next page, the I/O setup one. We also want to check Enable THC control since we will be using the torch height controller. I will also check Enable THC anti-dive. This is a value that can be entered on the bottom left while or before cutting. This is a percentage value that will minimize quick downward movements. This helps around corners where the voltage might experience a quick drop. The next page will not be any use to us, but the setup page contains the auxiliary encoder settings and the M10X M11X fast synchronous output settings. To try to quickly summarize what is in the trigger page, the I trigger will essentially activate whenever an input is triggered. We set a function to also follow. For example, if we want coolant on every time the probe is touched. The output triggers work very similar. Whenever an output is triggered, a function will follow. For example, coolant on with pin 8 or the torch on pin. The hotkeys page is to create key bindings on your keyboard to a certain function. For example, left arrow is jog X in the negative direction. The next page is our diagnostic tab, which will give a visual representation of all the inputs and outputs, whether they are on or off. On my page, we can see or input 1 and input 2 are active, which means there is 24 volts for the e-stop and probe. However, since we have an active low condition, that means the e-stop and probe are not active as shown under the middle column. Lastly is a cam tab, which I do not use. It will generate simpler G-code based on a DXF drawing. Don't forget to like, comment, and subscribe.